Good morning, everyone. My name is Wahyuni Ekasari from Institut Teknologi 10 November and Politeknik Negeri Samarinda. This is joint work with Miss Erma Suryani and Miss Amalia Utamima. Today, I present a systematic literature review on the role of AI methods and input variable selection in time series prediction for smart irrigation. We follow Prisma 2020. From 99 initial records, we include 31 primary studies published between 2021 and 2026 and use them to answer three research questions. Let me start with why this review was needed. In precision agriculture, almost every variable we care about is time series data, soil moisture, evapotranspiration, and crop water demand. The method have moved very quickly from classical machine learning to deep learning architectures with temporal memory such as LSTM, GRU, and conventional LSTM, and now to hybrid models. But the field has moved faster than the evidence. We still do not have a clear picture of which method perform best in which context or whether the added complexity actually pays off in accuracy. So our objective was to characterize the best performing prediction algorithm for smart irrigation time series and to map how method, input variables, and hybridization strategies relate to performance. The review makes four contributions. We map the three method families against predictive performance, synthesize the rule of input variable selection, evaluate how far hybridization pays for its computational cost, and propose a standardized benchmarking checklist. Okay, those contribution trends into three relational research questions. So for research question one, is there a relationship between the type of method, machine learning, deep learning, or hybrid, and predictive performance measured through accuracy, RMSE, MAA, and R square? And the second research question two, does the selection of input variable affect model accuracy and generalization? And the last research question three, do optimization method, genetic algorithm, attention, or fuzzy logic deliver real gains in performance and computational efficiency? Now the protocol we search Scopus database with Boolean query combining smart and precision irrigation and water demand with deep learning, LSTM, GRO, and time series restrict to restrict to English language journal articles from 2021 to 2026. Screening use Mendeley and Watasa Owake web application following our inclusion and exclusion criteria as the Prisma flows shows. 99 records were reduced to 31 studies. Extraction used double coding by Curator with a shared codebook. Importantly, relative improvement was always computed against the strongest baseline each study itself report. For synthesis, we use descriptive statistic and fault counting. A full meta-analysis was not feasible because metric and baseline were too heterogeneous, a point I will return to. To the first research question, one clarity before the number. This describes tendency across studies, each relative to its own baseline. They are not full effect size. Deep learning and hybrid approach account for 30 each study, each and classical machine learning for 5. Mean relative improvement was 28.5% for deep learning and 30.2% for hybrid models, against 1.8% for machine learning. The largest single gains was 89.5% over an LSTM baseline from a modified transformer hybrid for water demand forecasting. Among best architectures, recurrent networks dominate, followed by transformer and attention-based model, then tree-based models. But in this method for practice, machine learning stays competitive. XGBoost and like GBM outperform both deep learning network and LSM on irrigated land and random forest reach a validation R square above 0.98. On the reliability of on-coding, iterator agreement was almost perfect with Cohen's kappa of 0.895 with agreement 29 of 31 studies and 29 studies explicitly model temporal dynamics with daily resolution on the most common horizons. And how about the research question two? The second research question is about input variables, and the headline is simple. Relevance matters more than quantity. 23 of 31 studies combine three families of inputs: meteorology, soil properties, and temporal history. The median is around 7 features. Tutoring is very wide. The table summarizes what happened when studies modify those inputs, adding surface soil moisture raised R squared from 0.73 to 0.85 and cut RMSE by 70 kilograms per hectare. One study compared 17, 14, and for feature 14 was optimal, so more was not better. Fuzzy selection kept 7 of 23 rules and 4 of 18 feature, preserving accuracy at lower dimensionality. One further observation studies that generalize successfully use slightly more feature, a median of 7 against 5. The goal is not the smallest feature set, but the right side. And the third research question concern about optimization and hybridization. 20 of 31 studies combine a best predictor with at least one auxiliary component. Attention, the composition, and meta heuristic are domain knowledge. The table shows report K next to computational costs. At the top, a transformer with fuzzy logic and NSGA2 reach plus 89.5% at high cost, a linear non-linear fusion CAF plus 66% or moderate cost, causal attention with PCMCI CAF plus 62.3% but required 6 GPUs. Then an important exception, the informer unit reached plus 43.4% at low cost with only 1.17 million parameter. So overall, a hybrid pipelines report higher means gains 30.1% against 18.5, but almost always with an efficiency trade-off. So the best efficiency does not come from stacking algorithm. It comes from architecturally clever design, a proprietary assemble, for example, cat parameter complexity by about 78%. Okay, the next is evaluation method and research gap. This brings me to how these models are evaluated and to the central problem of the fields. R squared is the most frequent matrix in 10 studies, followed by RMSA, MAA, accuracy. Validation is dominated by whole out combined with temporal splits. The appropriate choice here because temporal splits preserve chronological order and prevent leakage. K-fault is rare and risk violating temporal causality. Several studies report neither a numerical baseline nor any measure of efficiency. From this, we identify five gaps: transferability, computational load, knowledge-driven, standardization, and long horizon. Long horizon. In response, we propose a checklist of 7 minimum reporting conditions. Um, yeah, this is a benchmarking checklist. A persistent baseline plus one standard temporal deep learning baseline on identical inputs RMSE and MAE in physical units plus R square with the primary metric state in advanced chronological splits with explicit horizons report parameters, training and inference time, and hardware evaluation on at least one unseen site, session, or year, release code or full hyperparameters, and at least one interpretability analysis. Okay, in the last, to conclude, forecasting effectiveness depends jointly on the method, the variables, and the development approach. For RQ1, deep learning and hybrid models were consistently associated with higher reported accuracy than classical machine learning, in line with their capacity to capture complex temporal patterns, but ensemble machine learning remains viable where data or computing resources are limited. For RQ2, the relevance of input variables matter more than their number, with soil moisture, evapotranspiration, and remote sensing data the most valuable inputs for both accuracy and generalization. For RQ3, attention, decomposition, meta-heuristic, and knowledge guidance report larger gains than standalone models, but a higher cost and without match experimental condition. And our limitations are clear, so most studies are confined with specific locales and climate, so transferability is unproven. The most accurate models are computational intensive and varying baselines, and metrics hampers comparison too. So future work follows directly. We aim for models that are accurate, generalizable, and efficiency. Reports against standardized criteria. That means cross-region and cross-climate testing beyond Scopus, embedding physical and cultural knowledge into architecture, explainable AI for operational trust, and live-wire model for each device and field sensor. So thank you very much for your attention. I will be happy to take your question. See you, everybody.